Welcome back. Let's get some practice with spherical coordinates. I've written down the additional equations that we just discussed in the previous video. And now we're going to practice changing coordinates. So given a rho, theta, and phi, we can plug those into our equations. We get that x equals 2 times cosine of pi over 4 times sine of pi over 3. We get that y is equal to 2 times sine of pi over 4 times cosine of pi over 3. Sorry, times sine of pi over 3. And we get that z is equal to 2 times cosine of pi over 3. So we can evaluate those directly. We can also get Mathematica to do that for us. And we'll go over and do that. Let's just look at this other example. If we start out with x, y, and z, with -1, 1, and root 6, then we would plug into the other equations and we would say, okay, so rho is equal to the square root of 1 squared plus 1 squared plus root 6 squared. So that's going to be the square root of 8. And then we're going to have the tangent of theta is equal to 1 over -1. So that gives us that theta is equal to negative pi over 4. Of course, we're in the other quadrant, so that's actually going to be 3 pi over 4, because we need to be in the quadrant where x and y are positive, or where x is negative and y is positive. And the last thing is we have tangent of phi is equal to square root of 2 over square root of 6. And so this is going to give us our values. Let's go over to Mathematica and we'll get it to do it. So I've set up this notebook so that you can, these are the equations that convert between x, y, and z. So if you plug in your x and your y and your z, what do we get? X is equal to -1, y is equal to 1, z is equal to square root of 6. Then that's going to give us that rho is equal to root 8. Theta is equal to negative pi over 4. I think I'm actually going to fix this by making it arctan of x comma 1. Right, so there are two different versions of arctan in Mathematica, and in this case we can use a different this other version, which gives you the signed version of the arctangent. Let me update that down here too. So rho, theta, and phi give you the correct rho, theta, and phi now. And then similarly, if we plug in rho is equal to 2, theta is equal to pi over 4, and phi is equal to pi over 3, then this is going to give us that x is root 3 over 2, sorry, y is equal to root 3 over root 2, and z is equal to 1. So that gives us the x, y, and z coordinates for that. Alright, so that's some practice changing coordinates. Now let's go and identify some special spherical coordinate equations. Alright, so when we have phi is equal to pi over 3, what that's doing is that's specifying what the angle is. That is the angle coming down from the positive z-axis. And so if that stays constant, then if we rotate it around the z-axis, what we're seeing is phi is equal to a constant corresponds to a cone of a fixed angle from the z-axis. So this is a cone, and we can apply this formula if we wanted to, and we could say, so tangent of pi over 3 is equal to square root of x squared plus y squared over z. Or in other words, we get that z, So tangent of pi over 3 is root 3. So z is equal to 1 over root 3 times square root of x squared plus y squared. Or in other words, z squared is equal to 1/3 of x squared plus y squared. And there we're really seeing the cone pop out at us if we want. All right, here's another equation. Rho sine of phi is equal to 2. So this is where we use our r, and that's r sine of phi. And so this is basically, this equation is r is equal to 2. So rho sine of phi equals 2 is a cylinder that has radius 2. Right, but let's contrast that with rho is equal to 2 cosine phi, and that is giving us z is equal to 2. So that's an equation that is z is equal to, sorry, 2 cosine phi. Sorry, I got a little bit excited there. So rho is equal to 2 cosine of phi. So if we multiply both sides by rho, we get rho squared is equal to 2 rho cosine of phi. And so rho squared is x squared plus y squared plus z squared. 2 rho cosine of phi is equal to 2z. And so then this is going to be, so if we take x squared plus y squared plus z squared minus 2z, and add 1 to both sides, what we see is we get a sphere that's centered at 0, 0, 1. So this is applying the different formulas that we have to convert things into x, y's, and z's. So now let's go over to Mathematica and see those things in action. So we can use simplify, or we can plot these equations directly. So let's say we had something that looked like phi, sorry, rho times sine of phi. Sine of phi. Rho times sine of phi, if we put that in here and put all our simplifications in there, we get this expression, which is rather ugly. That's not being as helpful as I would hope it would be. So maybe that's a case that's telling us maybe we should do a plot. So unlike cylindrical plotting, spherical plotting does exist already in Mathematica. So if we want to plot rho as a function of sine of phi, or of phi and theta, we can do that. So let me talk about our equation. We had rho times sine of phi was equal to 2. So we're going to convert that into the equation. Rho is equal to 2 divided by sine of phi. So we're going to put this as the equation here. We want to plot 2 divided by sine of phi. And when we do that, it's not giving us anything. Why is it not giving us anything? What did we say this was? This was sorry, because if this r is equal to 2, Here, a plot of 2 divided by sine of phi for different values of theta, different values of phi. And maybe my plot range is too small. Yes, that's what it is. Whoa. Well, that's not what I was expecting to get, since we expected to get rho sine of phi, which is r, is equal to 2. We're expecting a cylinder. All right, well, let's look at the next one. The next one was rho is equal to 2 cosine of phi. And if we plot that, I'm wondering if my thetas and phis are wrong, in the wrong order. Let's see. Theta is supposed to be first, and phi is supposed to be second. Let's see what happens if I switch them. Oh, that was the problem. It uses theta and phi the wrong way, or the opposite of what we're talking about. Ah, now it's giving us what we were hoping. So, the key thought. Oh, all right. So, in spherical plotting, just learned this now, is that the Mathematica's conventions for theta and phi are backwards, are reversed. When we think of theta, they think of phi. And so the way we can just fix that is we just type it in normally. We just switch the order of phi and theta, and that's going to give us our equation that we want. So this gives us indeed the ball that we cared about and the cylinder that we cared about. As an example here, I came up with one more thing, so this one's interesting, where we look at sine of 4 phi cosine of 3 theta, so that's some sort of like oscillating thing. If you plug those in, you get this interesting multi-lobed snowflake. And if you want to just choose one, you can restrict what your bounds are on theta and phi. So remember, since these are backwards, what we really have is this as our equation, and we have this as our, this one is the, just have this here. This is what happens when you play around with things and you're not 100% sure what's going to happen. So these are our phis and thetas. So let's update this equation. And so we had phi should go from 0 to pi, and theta goes from 0 to 2 pi. And we get this snowflake. I think that's enough video for now. Let's go, we'll start another video shortly. See you soon.